Okay, yeah, let's continue. I think is another part. We just had a technical glitch. Yeah, I was still talking about the 5 factors that affect the reaction rate. Started with temperature. We said the higher the temperature, the faster the reaction rate, and concentration as the second one. We say the higher the concentration, the faster the reaction rate as well. And then number 3, about the catalysts. I'll just mention one reaction where all these are applicable. A catalyst, remember, we'll talk about positive and negative catalysts here, and the addition of a suitable catalyst. Addition of a suitable catalyst increases the reaction rate. Very simple. Now the fourth one is about the state of division, or what we call the surface area, the area of the reacting surface. Therefore, in this one, we just summarize it by to say the finer the substance, and the faster the reaction rate. Why do you prefer a powdered grandpa than the tablets? The reaction rate. That's because of this one. So you crush food before swallowing them. Yes, because once they are stately divided, then it will be easier to swallow them. If you look at this equation, which summarizes all this, I've got magnesium ribbon, and then react with HCl, 2 HCl, obviously, forming MCl2 plus hydrogen. If you want to form hydrogen in the lab, you just react normally acid with a metal. Fine. This one, let's say, has got 0.5 mole per dm cube. Experiment 1. Experiment 2, I use the powder, and then still with 0.5 concentration here. Reaction 3, let's say at 25 degrees Celsius, 25 degrees Celsius here. And then reaction 3, I use the ribbon. Now it's 2 mole per dm cube, and then still at 25. And number 4, I use a ribbon or maybe powder, 0.5, but I use 40 degrees Celsius here. Yeah, thank you. Fine. I'll talk about the 5th factor because normally it will come after this one. If you look at the experiment 1, if I compare experiment 1 and experiment 2, temperature is the same, concentration is the same, then I only compare the state of division of magnesium here. Therefore, ribbon and powder, therefore powder will be faster than the ribbon. If I compare 1 and 3, ribbon, temperature is the same, but look at concentration. This one is half, this one is 2. Therefore, it means that now reaction 3 will be faster than reaction 1. If I compare reaction 2 and 4, powder, concentration is the same, but look at the temperature. Then it means that now reaction 4 will be happening at a faster rate compared to reaction 2. Now bring me to the last factor, the nature of the reacting substance. Nature of the reacting substance. This one normally fiddle with the reaction now. I have to change. If I can use zinc, in this case plus HCl, and forming zinc chloride, plus hydrogen. Now they ask you which one will happen at a faster rate. Now I'm going to look at the reducing ability of these two. Now which one is a stronger reducing agent? If you go to the table, you find that magnesium is saving somewhere around negative 2.36 a volt, whereas zinc is saving somewhere around negative 0.76 volts. Therefore, which one is a stronger reducing agent? Will be magnesium. Magnesium will be a stronger reducing agent than zinc. Therefore, in the case of magnesium, if I've got two beakers here where the experiment is taking place, I put magnesium here, Mg, and then I put zinc here, Zn. This is the case, very important. If I've got HCl and HCl in both as the solution or the electrolyte here, fine. Then it means that now I will have more bubbles in the magnesium one, whereas in the zinc I will have very few bubbles. That is the case. Therefore, it means that now magnesium is a good reducing agent compared to zinc. Therefore, magnesium is more reactive than zinc. That's what happens. So that's all about the nature of the reacting substance. Fine. When you deal with that one, then that's what we'll be talking about. So I've already mentioned the other examples here, which is very good again. Now, before we come to real questions now, let me just touch base where now we talk about measuring the reaction rate now. So where we measure this reaction rate. Let's say, for example, we have got, in this case, let me just make it portrait this one. Mechanism of the reaction rate, mechanism of reaction of a reaction. Thanks. Let's say we just take calcium carbonate, 2HCl. Now here we will be using the stoichiometric calculations. Hopefully still remember quantitative aspects in chemistry. In this case, carbon dioxide will be the product as well. Yes. Now this is the reaction. Calcium carbonate react with acid, hydrochloric acid, and produces calcium chloride, water, and carbon dioxide. Now let's say in one question they told learners about this one, to say I've got a cotton wool here, cotton wool, and then the bubbles are here, fine, and they've got the reactants here, the calcium carbonate and HCl and calcium carbonate. Now there is the so-called the mass meter. Mass meter is here. Now hypothetically, let me just come up with this delta T, and then this will be the case of mass, and then when time is 0, I had 200 grams, and time is 1 minute, then I've got 198, and time is 3 minutes, I've got 192, and time is 5 minutes, I've got 189, when time is 7 minutes, then I've got 186. Let's say this is the results. Now they say to the learners to say now, oh fine, name the substance from the reaction which is responsible for this decrease in mass of the container. when we measure this one in different times, this is what we get. What causes this? So it means that now carbon dioxide, the gas is released from the container. Why the gas is released? Then comes this use of a cotton wool. The cotton wool is used just to trap any other substances here except the gas, just to allow the gas to pass through, and other substances will be trapped inside the beaker. Fine. Now, what is the mass of the gas here that was released in 7 minutes? Then the mass will be now the 200 minus 186, which give us somewhere around 14 grams. No problem. Now, if this is the mass of the carbon dioxide that left the container, calculate the mass of calcium carbonate that was used in this case in the 7 minutes. So you can do that if you know your stoichiometric calculations, knowing that now I've got only 14 grams of carbon dioxide here that left the container. Now, if I've got mass, I can calculate moles. Yes, that's one option, because the other option, then I can use mass calculation, which is quicker. But let's go the normal route to say, first calculate the number of moles of carbon dioxide. Number of mole of CO2 will be given mass over the molar mass, which is the same as 14 divided by 44, and then it gives you somewhere around 0.3 something. So let me make the one that is user friendly, 182, and then 182, and then I've got 18 instead of the 14. Sorry for that one. So I get 0.4, 18 this one, then I get 0.4, fine, 0.4 moles. Now when you've got 0.4 moles, calculate now the number of mole of this one, calcium carbonate. According to the balance equation, number of mole of calcium carbonate equals to number of mole of carbon dioxide. They are in the ratio 1:1. Therefore, this will be the same as 0.4 mole. Fine. Then I know the number of moles. With mole, I can find mass. Yes, mass of calcium carbonate. It will be the same as number of mole multiplied by the molar mass, which gives us 0.4 multiplied by 100, then which will give us 40 grams, around 40 grams, no problem. 40 grams, 40 grams. So that is, you use 40 grams for 7 minutes, so that the gas that is released is 18 grams out of the whole thing. Fine. So that's when now use stoichiometric calculations now to solve your problem. So I think we'll deal more with this type of questions when we'll be now dealing with questions where now involving measuring the rate of reaction. So that is the mechanism of a chemical reaction here now. When the reaction proceeds, what happens? You can represent this one using a graph. We represent this one now here using a table. So there are many ways that this can be unfolding. So the bottom line is that know that if I put mass in a balanced chemical equation, I can determine moles, I can determine whatever. So that's the case. Until we meet again in the next session, thanks a lot. I hope it's becoming clearer and clearer now. Thank you.